Right, let's get straight to it. We are powering up your exam readiness for Physical Sciences Paper 2 today. In this comprehensive explainer, we're going to break down real past paper questions, figure out exactly what those examiners are hunting for, and make sure you've got the clear, step-by-step strategies you need to absolutely secure those top marks.
Here is our game plan for today. We'll kick things off by mastering organic chemistry, then dive into reaction rates and graphs, tackle chemical equilibrium shifts, break down acids, bases, and pH, and finally wrap up with my absolute top exam tips. Section 1, Mastering Organic Chemistry. We're breaking down formulas, isomers, and homologous series. Okay, look at this definition. Unsaturated compound. An organic compound containing double or triple bonds between carbon atoms. Now, examiners absolutely love testing definitions, so you want to lock this one in your memory right now to grab those easy initial points. When they ask for it, don't just paraphrase it or give a vague idea. Write it down exactly like this. Knowing your definitions cold gives you a massive confidence boost right at the start of a tricky question.
Next up, we have positional isomers versus chain isomers, and knowing the difference here is a real game changer. Think of positional isomers as just moving the furniture around. The functional group shifts its position, like a hydroxyl moving from carbon 1 to carbon 2, so the number in the name changes. But with chain isomers, you're actually remodeling the house. The main carbon backbone gets shorter, and you end up with branches, like methyl groups. Keeping these two concepts totally distinct will save you from making silly mistakes.
All right, time for our first interactive moment. Pause the explainer right here and test your knowledge before I give it away. Look closely at that formula, CnH2n-2. Think back to your functional groups. Got your answer? It's an alkyne. Recognizing these general formulas instantly is literally going to save you so much time, especially in the multiple choice section. Now check out this data pulled straight from a past paper comparing aldehydes and carboxylic acids. You can see a super clear trend here, right? Notice how the boiling point just shoots up as the carbon chain gets longer in both groups? Why does that happen? Well, as the chain length increases, the surface area of the molecule increases, which leads to stronger intermolecular forces, specifically London forces. But hold on, look at the staggering difference between the two series. Carboxylic acids boil at way higher temperatures because they form really strong hydrogen bonds, whereas aldehydes are just working with weaker dipole-dipole forces. Moving right along to Section 2, Reaction Rates and Graphs. We'll be looking at collision theory and calculating volumes. Here is an exact balanced equation provided for an experiment testing aluminum carbonate reacting with excess hydrochloric acid. Remember, whenever you get a balanced equation on your exam, your immediate first instinct should be highlighting the molar ratios. See that? 1 mole of solid aluminum carbonate reacts with 6 moles of aqueous hydrochloric acid to produce 3 moles of carbon dioxide gas. Those numbers are your essential roadmap for the calculations that are definitely about to follow. Let's compare the actual reaction conditions. Experiment 1 uses a concentration of 1.5 moles per cubic decimeter, but Experiment 2 steps it up to 2 moles. Notice that both use the exact same amount of aluminum carbonate granules, 0.016 moles, and they're both sitting at 25 degrees Celsius. By laying the data out clearly like this, the independent variable is staring right at us. It's the concentration of the hydrochloric acid. Let's do another pause and predict. Based strictly on collision theory, how does the average reaction rate in Experiment 1 differ from Experiment 2? Hit pause and think about it. Ready? So because Experiment 2 has a higher acid concentration, you've got way more reacting particles crammed into the same unit volume. That means a higher frequency of effective collisions per unit time, making the reaction much faster. Make sure you use those magic examiner phrases, more particles per unit volume and more effective collisions per unit time. They love that. When you're asked to calculate the maximum volume of gas produced, you just need to follow these exact 3 steps for full marks. Step 1, jot down the given molar gas volume, usually 24,000 cubic centimeters per mole at room temp. Step 2, figure out your limiting reagent. Since the acid is in excess here, our aluminium carbonate is the limiting factor. And step 3, use that 1 to 3 molar ratio we found earlier. Multiply your 0.016 moles of carbonate by 3 to get the moles of CO2. Then multiply that by your gas volume. Boom! Stick to the sequence and you'll never get lost in the numbers. Section 3. Chemical equilibrium shifts. Let's navigate Le Chatelier's principle.
Here is the golden rule of equilibrium. When a chemical system at equilibrium is disturbed, the system will shift its equilibrium position to counteract the effect of the disturbance. So, the crucial question you always have to ask yourself is, What is the system trying to undo? If you crank up the heat, the system tries to cool things down by favoring the endothermic reaction. If you increase the pressure, it shifts to the side with fewer gas moles to relieve that pressure. Master this logic, and interpreting those complex graphs becomes a total breeze.
Pause the explainer again. This is a classic graph interpretation question to see if you truly grasp dynamic equilibrium. When you see concentration curves level out and become completely parallel to the x-axis after, say, 5 minutes, what is that data telling you? If you said the system reached dynamic chemical equilibrium, you hit the nail on the head. It means the rate of the forward reaction perfectly matches the rate of the reverse reaction, so your concentrations are locked in and constant. Let's apply Le Chatelier's to a tricky exam scenario. Say a past paper states that heating a flask actually decreases your product yield. What's the hidden message there? Well, if adding heat lowered the yield, the system must have favored the reverse reaction to absorb that extra heat. That means the reverse reaction is endothermic, which means, actually, scratch that, let's say it clearer. If the reverse is endothermic, the forward reaction has to be exothermic. Tracing the logic backwards step by step like this is exactly how you keep your cool under exam pressure. All right, Section 4, acids, bases, and pH. We're looking at protons, amphiolites, and identifying strength. The Lowry-Bronsted theory defines an acid as a proton donor and a base as a proton acceptor. Now remember, a conjugate base is born the exact moment a proton is ripped away from the acid. Take hydrochloric acid. It donates a proton and leaves behind a chloride ion. That chloride ion, that's your conjugate base. Visualizing this simple game of proton ping pong is really the core of understanding all the acid-base reactions you'll see in paper 2. Check out this classic comparison setup. We're looking at two acids, HX with a pH of 2.7 and HY with a pH of 0.7, both at the exact same concentration. Which one is stronger? It's definitely HY. That super low pH is screaming that there's a much higher concentration of hydronium ions in there. Basically, a stronger acid ionizes way more completely in water, dumping a ton of protons and aggressively driving that pH number down.
On this slide, we have a whole spread of aqueous solutions all sitting at a standard room temperature and a concentration of 1 mole per cubic decimeter. You've got strong acids like nitric and sulfuric acid, strong bases like sodium hydroxide, neutral salts, and a few weak acids and bases mixed in. Being able to scan a list like this and instantly categorize who is who is an absolutely vital skill for the exam.
Let's put that to the test with our final pause and predict. Scan this table. Can you spot the weak diprotic acid? And which one is going to give you a perfectly neutral pH of 7? Pause and take a look. All right, the weak diprotic acid is oxalic acid. That's the COOH2. We call it diprotic because it can donate 2 protons. And the perfectly neutral one? That's our old friend, sodium chloride, NaC. Finally, Section 5, top exam tips for securing your absolute best Paper 2 mark. Listen up, because sticking to these strict examiner rules is how you scoop up every single easy mark. First, always show your full formula substitutions. You literally get a point just for writing down the correct formula before plugging in any numbers. Second, memorize your definitions word for word. Third, use step-by-step logic for rates in Le Chatelier's. State the change, state the effect on the particles, and conclude. Next, do not round off your numbers too early. Save that for your final answer and keep it to a minimum of 2 decimal places. And lastly, when investigating reaction rates, always clearly state what conditions you're keeping constant for a fair test. So we've covered a ton of ground today. You've got the formulas, the logic, and the step-by-step strategies. The only question now is, which complex chemistry topic are you going to conquer first today? And how is applying these strategies going to completely transform your final score? Are you going to master those rotating organic structures first, or jump straight into calculating reaction rates? Approach these papers with this exact step-by-step mindset, and you'll be unstoppable. Thanks for joining me on this explainer. Stay incredibly focused and go crush that physical sciences exam.